I'm just going to live stream, begin the live stream. Okay, maybe we can wait for 1 minute. Manjil, have you met Professor Bhatia? He's there.
No. Hello, Professor Bhatia.
And Bapat.
Sorry, I was muted. Hi, welcome.
Hello. Thank you.
And Professor Bapat is there too.
Yeah, we have met before, I think. Yeah, hello.
Yes, yes.
Yeah.
Hi.
Yeah, I think you spoke in ISI once.
Right.
Yeah, we met then, yes.
Right, right.
Okay, should I begin or? Manjil, do you want to share your screen?
Yes, yes. Okay, it's full screen, right?
Yeah, it's fine.
Okay.
So let me introduce you. So hi everybody, it's a great pleasure to introduce Manjil Saikia. He got his PhD from the University of Vienna in 2019, and currently he's a postdoc at Cardiff, in Cardiff University. So he works in the area of algebraic combinatorics. In particular, he works in the area of alternating sign matrices. So today he will be talking about parity biases in partitions and restricted partitions. So, on to you, Manjil.
Thank you, Gaurav. Thank you so much for the invitation. And also to everyone present here, thank you for coming. So this is something that, as Gaurav mentioned, that this is not my main work. So this is something that I got interested in recently, partitions and Q series. And I'm going to speak about a very new sort of like results that have been coming up in this area of partitions. So this is based on two papers. One is with Kaustubh Banerjee, Sri Rupa Bhattacharjee, Manashish Ghosh Dastidar, and Pankaj Jyoti Mohanto. And this should be out on archive today. And the other one is still not out. So it's with Pankaj Jyoti Mohanto and Abhishek Sharma. And all of these are actually quite young students. So Sri Rupa is starting her PhD now. Manashish is also probably starting his PhD soon. Abhishek is starting his PhD now, and Kaustubh is about to complete his. And Pankaj is been a close collaborator for the last few years. Anyway, so let's begin with some basic ideas. So I have to apologize for the experts in the audience because the first part would be a bit of crash course on partitions. So if you already know about partitions, then this might not be so interesting. Anyway, so let's define what is a partition. So for me, a partition lambda is a sequence of non-negative integers, lambda 1, lambda 2 up to lambda L, such that these are non-negative, these are weakly decreasing. So lambda 1 is greater than or equal to lambda 2 and so on up to lambda L. And if you sum over all the lambdas, then d is equal to n. So if these conditions are satisfied, then I say that lambda is a partition of n. And the set of all partitions is denoted by capital Pn, and the cardinality of this set is small p of n. So for example, there are 5 partitions of 4. Because 4 can be written as 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So these are the 5 partitions of 4, and we write P of 4 is equal to 5. So what about the generating function for P of n? So let's denote this by capital P of Q, and this is the so this is I mean, you can take it as a sort of definition of the generating function. So here for me, every time a series of this sort appears or a product will appear involving Q, these are all formal series or formal products. So you can think of them as infinite degree polynomials. And we can add, subtract, multiply all of these infinite degree polynomials then. Right. So Euler was one of the first pioneers of partitions, and he proved that the generating function for partitions is actually given by a very nice product. So the sum can be expressed as a very nice product. Let's look at how one can prove Euler's result. So it's not very difficult. Let us consider the first two. So this is an infinite product, and it starts from 1 over 1 minus q and then goes to 1 over 1 minus q square and so on. So let's focus on the first two factors of the product. So 1 over 1 minus q and 1 over 1 minus q square. So if I expand this using the geometric series formula, we get something like this. So this is the expansion of 1 over 1 minus q, which is 1 plus q square and so on. So this q square, q cube, I'm writing it as a sum. So q square, I'm writing it as q1 plus 1, and 1 plus 1 plus 1 for 3 and so on. And similarly, if I expand 1 over 1 minus q square, then I can write it as 1 plus q square plus q to the power 4 and so on. And again, this all the even powers, I'm writing it as sum of 2's. So 4 is 2 plus 2 and 6 will be 2 plus 2 plus 2 and so on. Now this equals, so if I just multiply them out now, and if I just take the common exponents together, so q square, if I take all the terms involving q square, and if I take all the terms involving q cube and so on, then I'll see that the series will be something like this. So 1 plus q to the 1, plus there will be two terms involving q square. So one will come from this q square here, and the other one will come from the 1 plus 1, so q1 plus 1. And there will be two terms involving q cube. So one will come as a result of multiplying this with this, and the other one will come from here, so multiplying this with the 1, and so on. So this is clearly the generating function of all possible partitions using only 1's and 2's, because the exponents can all be written as sums of 1's and 2's. Okay. And this is just for the first two factors of the product. So we can keep on doing this actually for all the products. So if we include the third factor, that is 1 over 1 minus q cube, then it will generate all possible partitions using only 1's, 2's, and 3's as parts. Okay. And we now do this for all products, and then we can find Euler's result, so which is the generating function for all partitions. Right. So there are many other types of partitions that are of interest. Also for this talk, some other partitions are of interest. So for example, if we only allow distinct parts in the partition, then we call such partitions as distinct parts partition. For example, these are the two distinct parts partition for 4. So here 2 plus 2 cannot appear as a partition because the parts are repeated. 2 is repeated twice. And similarly, if 1 is a repeated part, for example, in 2 plus 1 plus 1 and 1 plus 1 plus 1 plus 1. So these are not distinct parts partition because they are repetition of parts. So we denote this by small d of n. If we allow only odd parts in the partition, then we call such partitions as odd parts partition. For example, these are the odd parts partition for 4. So 3 plus 1 and 1 plus 1 plus 1. And it is not a coincidence that this d of 4 is equal to O of 4, because the number of distinct parts partition 4 is 2, and odd parts partition is also 2. So it's not a coincidence. We'll see a nice proof of that result soon. So another type of partition which is of interest in this talk is are called overpartitions. So in overpartitions, we allow the first occurrence of a part to be overlined. Then such partitions are called overpartitions. So for example, these are all the overpartitions of 4. So we already know that there are 5 partitions of 4, but now it turns out that there are 14 overpartitions of 4. So this is the first partition of 4, which is just 4. And we overline the first occurrence of a part, so which is this one. Okay, 4 bar is an overpartition where the first occurrence of 4 is overlined. Similarly, 3 plus 1 is a partition of 4. Now we overline the first occurrences of the parts. So here in the first 3 plus 1, in the first 3 is overlined, and here the first 1 is overlined, and in this the first occurrence of 3 and 1 both are overlined. And we keep on doing this for all of the other partitions. So for example, in this last case, there are 4 ones, and we just overline the first occurrence, which is a 1 here. Okay. So I can see that there is something in the chat. Okay, I see. So we denote this number of overpartitions by p bar of n, okay, or p overlined of n. So I mentioned that the number of distinct parts partition of n and the number of parts partition of n are equal, and this is a result of Euler. So we are going to see how to prove this result, because it's a very nice generating function proof. So the generating function for the distinct parts partition, we can write it as a product of 1 plus q to the I, where I runs from all possible values. Okay, and why is this the case? So in a distinct parts partition, every part, so every number that you take, so suppose you are trying to find the distinct parts partition of 7, and then you look at 1. So either 1 can appear as a part, or it does not appear as a part. You look at 2, either 2 appears as a part or it does not appear, and you keep on doing this until 7. So either 7 appears as a part in the partition or it does not. So this is translated into the generating function as 1 plus q to the I. So 1 is for the case where a part does not appear, which is basically q to the 0, and q to the I is the case where a part appears in the partition. And if you take the product of all the values of I, then you will see that this is just the generating function for d of n. Now using the high school formula, a square minus b square is equal to a plus b times a minus b, we can write this. We can write the generating function in this way. Okay, so I'm here just multiplying the numerator and denominator by 1 minus q to the I. So this 1 minus q to the I in the denominator, I can further write this as a product of over all the odd numbers as well as the even numbers. Okay, so I just break this into 2 factors, 1 minus q to the 2i minus 1 and 1 minus q to the 2i, and now I can just cancel out the 1 minus q to the 2i's from top and below. So I'm just left with this product 1 over 1 minus q to the 2i minus 1, and now this is just a generating function for partitions with only odd parts. So if you remember the generating function for partitions, all the partitions, then this was just the product of 1 over 1 minus q to the I. Now here the q to the I is replaced by q to the 2i minus 1. That means only odd exponents of q are considered here. So this will just give rise to partitions where only odd parts appear. So this is basically the generating function for odd parts partition. And since these 2 generating functions are equal, so we can just take consider the coefficient of the nth term, and we'll see that dn is equal to 1 for all cases. Okay, so this is a very nice generating function proof of Euler's result. There are combinatorial proofs as well, but I'm not going to do it here. So if someone is interested, then they can think of trying to do a combinatorial proof, which is not very difficult for this theorem at least. Okay, so what about the overpartitions? So remember, overpartitions were partitions where the first occurrence of a part can be overlined. So these were introduced by Jeremy Lovejoy and Sylvie Courtil in 2004, and they showed that the generating function for overpartitions is given by another nice product formula. Now this product you can already recognize both the numerator and the denominator in this product. So the numerator 1 plus q to the I, if you take the product of only the numerator, these are the this is the generating function for distinct parts partition, which you saw in the last slide. And if you take just the product of the denominator 1 over 1 minus q to the I, then this is just the generating function for all partitions. So I mean, we can exploit this. So since we already know the generating function from the result of Courtil and Lovejoy, it's not very difficult to see why this is true. Okay, so for any overpartition, you can actually form a partition with the non-overlined parts and a distinct parts partition with the overlined parts. So if let us go back to the example. So here, if you look at the non-overlined parts, then these are just normal partitions. Okay, so for example, here, if you look at the non-overlined parts, 1 plus 1 plus 1, this is just a partition without any restriction on it. but if you look at the overline parts, then there is a restriction that the parts have to be distinct. So for example, this is visible here in the 3+1 overline partition. So here both the 3 and the 1 are distinct parts. Okay, and this is true for all other partitions. So for example, here as well, 2+1+1 is a overpartition where the overline parts 2+1 forms a distinct parts partition, and the non-overline parts is just an unrestricted partition. There is no restriction on that. So because of that, the genetic function for all overpartitions is just a product of 1 plus q to the I times 1 over 1 minus q to the I. So this 1 plus q to the I will generate the overline parts, and 1 minus q to the I will generate the non-overline parts. Okay, so I mean, there are like I don't know, so there are like hundreds and thousands of partition identities, some of which can be proved using genetic function results, and some of which needs combinatorial techniques to prove. So I mean, as I said, that this is just like a basic crash course on partition. So I just want to mention 2 results. If any of the students are interested, then they can take a look. So it turns out that the number of partitions of n with m parts equals the number of partitions of n with largest part m. Okay, so this is a very easy result that one can prove. I mean, either using genetic functions or combinatorial techniques. A much more difficult result would be the next one, so which is a result of Lagrange and Euler. It says that the difference between the number of partitions of n into an even number of parts, which are all distinct, and the number of partitions of n into an odd number of parts, which are all distinct, is always 0, except when n is of a very particular form, which is 3k squared by 2 plus minus k by 2. So this is another very famous result of Euler, and I mean, it would be a challenge problem, so to find a combinatorial proof or even a genetic function proof for this result. Okay.
Why did you say it's the Lagrange?
The combinatorial interpretation is by Lagrange. The genetic function proof is by Euler.
Right. Okay.
Yeah. So let's come to the main topic of the talk, which is parity bias on partitions. So far we have seen only equalities, so like dn is equal to on and so on. But inequalities also appear in the study of partitions. So for example, there are famous inequalities like Elder's conjecture. There are inequalities which arise from something called Rogers-Ramanujan identities and so on. But here I'm interested in much more simpler to state inequalities, so which are basically parity biases in partitions. Recently, Kim and Lovejoy, so the 2 Kims are Byung-Chun Kim and Oini Kim and Jeremy Lovejoy. They observed that partitions with more odd parts than even parts are more in number than partitions with more even parts than odd parts. So for instance, so let's denote the number of partitions where there are more odd parts than even parts by P sub O of n, and the number of partitions where there are more even parts than odd parts by P sub E of n. So for example, let's look at our favorite number 4. So P sub O of 4 counts the number of partitions where there are more odd parts than even parts. So these 3 partitions. So 3 plus 1 has only odd parts. 2 plus 1 plus 1 has 2 odd parts, but just 1 even part. And 1 plus 1 plus 1 has all odd parts. So P sub O of 4 is just 3. And P sub E of 4 is now 2, because there are 2 partitions where there are more even parts than odd parts. So 4 and 2 plus 2. So in this case, it happens that P sub O of 4 plus P sub E of 4 is equal to P of n, but this is not always the case. So there might be partitions where the number of even parts and the number of odd parts are equal. So in that case, those partitions are not counted by either of P sub O of En or P sub E of n. So in this very special case, it turns out that there are no such partitions where there are equal number of even and odd parts. Then Kim and Lovejoy, they proved that for all n not equal to 2, we always have that P sub O of n is greater than P sub E of n. Now this result is also intuitively clear, because once if you have more, so I mean, in all the partitions of n, any integer n you take, you can always break it down into ones, right? So, and these ones, they will always contribute more in number than other numbers. So if you break them into twos or threes or whatever, this will be less in number than ones. And so it's almost intuitively clear that P sub O of n should be greater than P sub E of n. And Kim and Lovejoy, they proved that this result is true for all n not equal to 2. So their proof was by using analytical techniques, some Q-series techniques, which uses classical Q-series identities. And so the first team with Banerjee, Bhattacharjee, Dastidar, and Mohanta, we gave a combinatorial proof of this result. So they also, Kim and Lovejoy, they also conjectured that if we restrict to only distinct parts, all the partitions, if we just consider the distinct parts partitions, then this parity bias is also true for distinct parts partition, but here it's only true for n greater than 19. So they conjectured that D sub O of n, which is now the number of distinct parts partition where odd parts are more in number than even parts, is greater than D sub E of n, which is again the distinct parts partition where even parts appear more in number than odd parts. So this was only conjectured by them. And we, the same team, we gave a combinatorial proof for this as well. So using analytic techniques, it's not possible to, I mean, maybe it's possible to prove, but we could not find one. So there are certain difficulties in doing the distinct parts partition parity biases using analytical techniques. So there are more, so some more parity biases are possible in restricted partitions now. For example, I was discussing this with Gaurav before the talk. So Lovejoy, he was giving a talk in December last year in a conference in India. And after the talk, Michael Schlosser, he asked a natural question: what happens if we do not allow one as a part in the partitions? Then is the parity bias true, or is it reversed, or what? So Schlosser made the observation that it's reversed for, I think he checked until n equal to 7 or 8 during the talk. And it turns out that the inequality is reversed. So Schlosser's observation was correct. And we gave a combinatorial proof for this as well. So what is the result? So if we only take the partitions of n where 1 does not appear as a part, that means the smallest part that can appear is 2, at least 2, then the inequality is reversed. So here Q sub O of n, it denotes the number of partitions of n with more odd parts than even parts, where the smallest part is at least 2. That means 1 is not a part. And Q sub E of n is just the other direction. So where number of even parts are more in number than odd parts, where 1 does not appear as a part. So in the earlier case, when 1 appeared as a part, this inequality was in the other direction, and now the inequality is reversed. So that means parity bias is somehow reversed for all n greater than 7. And again, this is intuitively clear, because if you remove the ones, then there will be less number of odd parts to work with. So if you just, because ones contribute a lot to the number of parts in a partition. Anyway, so we also gave a combinatorial proof for this result, for Schlosser's result. In fact, a much more stronger inequality is true. And this is now joint work with the other team, Pankaj Mohanta and Abhishek Sharma, where 3Q sub O of n is actually less than 2Q sub E of n for all n greater than 10. So these type of inequalities were also proven by Kim and Lovejoy for the unrestricted case, but those proofs were much more complicated than the normal inequality. And the combinatorial techniques, they don't really work to prove such kind of inequalities. Anyway, so there is a much more strong inequality for this case as well. So it's not only that we just remove one as a part and then we get parity biases. We can also do other kind of parity biases. So for example, if we take a non-empty subset S of the positive integers, then we denote this quantity P sub E superscript Sn to be the number of partitions, to be the set of partitions which belong to P sub E of n, that is the partitions where even parts are more in number than odd parts. But now we restrict the parts, so we don't want parts that that are in the set S to appear. Okay, and similarly, P sub O of n, we restrict the parts where we don't allow the parts in S to appear. Now, there are other results of the similar flavor. For instance, parity bias is intact if we remove just 2 as a part. Okay, so if we don't allow 2 as a part, then the original parity bias, where the number of partitions with more odd parts than even parts were greater in number than the number of partitions with more even parts than odd parts, is also true for this case. And in fact, if we remove 1 and 2 from the set S, from the parts of the partition, then we also get some sort of parity bias in this case. These theorems were again proved using combinatorial techniques, and I think our techniques, well, it does not exhaust, but it gets more difficult to prove after this point if we take bigger sets for S. Even analytical techniques, they don't really work very well if we take a set S other than 1, where S is equal to 1. So our proofs, they yield many theorems of similar flavor, which deals with parity biases. I mean, our proofs in the sense the analytical proofs that we did with Mahanta and Sharma. And for example, here is another result, which is, I mean, it's a mouthful, but it's very easy to prove using similar techniques. So here, let n be an even number, and capital E sub E of n is the number of partitions of n with even number of even and odd parts, where the number of even parts are more than odd parts. And O sub E of n is just the opposite. So where there are even number of even and odd parts, but now odd parts are more in number than even parts. Then we get some sort of parity bias here as well. So O sub E of n is greater than E sub E of n. So this is just one example of the type of result that we can prove, and there are many more. Actually, there are about 6-7 more sort of similar results that we can prove, and the proof technique is similar for all of them, because yeah. So I'll talk about the proof technique in a little bit, how we are going to prove this. So what about more general arithmetic progressions? Not only like partitions. I mean, there are results for more general arithmetic progressions as well. But I'll just mention one result by Kim and Kim. So the same Kims, Bingcham Kim and Uni Kim, they proved some more parity biases. So what they did was they took a more general class of partitions. So they considered P sub j k m of n, which is now the number of partitions of n such that there are more parts congruent to j modulo m than parts congruent to k modulo m. Okay, so then for instance, P sub 1, 0 of 2 is just P sub O of n. So where there are more parts congruent to 1 modulo 2 than 0 modulo 2. And similarly, P sub 0, 1, 2 is just P sub E of n, where there are more parts congruent to 0 modulo 2 than 1 modulo 2. So this is a sort of proper generalization of the earlier results of Kim and Lovejoy. So they showed that for all positive integers n, which is greater than or equal to m square minus m plus 1, they have this more general result, where they showed that the number of partitions of n where parts congruent to 1 modulo m are more in number than parts congruent to 0 modulo m. These partitions are more in number than the other side. So where there are more parts congruent to 0 mod m than 1 mod m. And it was then natural to ask Schlosser's question for these inequalities as well. What happens if we remove certain parts from the parts of the partition, allowed parts of the partition? And we, Mahanta, Saikia, and me, we showed that indeed the inequality is reversed if we do not allow one as a part. And this time the proof techniques were all analytical, because it gets very difficult to combinatorially. In fact, Kim and Kim, their paper is also only analytical proofs. So they prove actually more than what is stated here. They also give, so both the papers by Kim, Lovejoy, and Kim, they also give asymptotic results for the number of such partitions. And these are nice asymptotic results that they prove. But they use, I mean, pretty sophisticated techniques so to do this. Anyway, so what about overpartition? So can we ask about biases in other type of statistics? So far we have only considered the statistic where we're counting the number of parts of certain parity and showed that these parity biases occur. But there are other type of biases which also occur in partitions, specifically in overpartitions. So there was a result which was proven by Kim, and Lovejoy, and they showed that. So again, this is a mouthful, so just I'll give an example after this. So if P sub U of n is the number of overpartitions of n with more unoverlined parts than overlined parts, and similarly P sub O of n is now the number of overpartitions of n with more overlined parts than unoverlined parts. So this U means more unoverlined and O means more overlined. Then this difference, P sub U of n minus P sub O of n, is actually equal to the number of overpartitions of n, where the number of unoverlined parts is at least 2 more than the number of overlined parts. So let's look at an example which will make it a bit more easier to see. So these are the 8 overpartitions of 3. Okay, so there are 3 partitions of 3, which are 3, 2 plus 1, and 1 plus 1 plus 1. But there are 8 overpartitions of 3. Okay. Now, P sub U of n, it counts the number of overpartitions of n where there are more unoverlined parts than overlined parts. So let's look at that. So here 3, this partition will be counted in P sub U of n because there is not this. The first 3 will be counted in P sub U of n because there is a unoverlined part, but there is no overlined part. And similarly, 2 plus 1 will be counted here, and so on. 1 plus 1 plus 1 will be counted here. And if we do this for all, so for example, 1 plus 1 plus 1, this partition will also be counted. So if we do this, for all of these overpartitions, then we'll see that P sub U of 3 is equal to 4, and P sub O of 3 will be equal to 2, which are the partitions where there are more overlined parts than unoverlined parts. So for example, this partition will be counted here, and this partition will be counted here, 2 plus 1. Okay. Now, if you take the difference, then we'll get that the difference is 2, and this difference will now be equal to the number of overpartitions of n, where the number of unoverlined parts is at least 2 more than the number of overlined parts, and these will correspond to these 2 partitions, 2 plus 1 and 1 plus 1 plus 1. Since there are no overlined parts, so this is anyway true, whatever is stated in the theorem. Okay. So this is a bit more complicated bias than the parity biases which we're talking about. And it turns out that we can do a more refined version of this result in the sense that we define P sub BU of n, which is now the number of overpartitions of n with more unoverlined parts, which are multiples of B, okay, than overlined parts. And similarly, P sub BO of n is now again the number of overpartitions with more overlined parts, which are multiples of B than unoverlined parts. So Kim, and Lovejoy's result was for B equal to 1 because they were not considering multiplicity. They were not considering the factors of the overlined or unoverlined parts. Then, if we take the difference, like it was taken by it was taken in the other result, so we'll see that this number is again equal to the number of overpartitions of n, where the number of unoverlined parts is at least 2 more than the number of overlined parts. So this is sort of like a more refined version of the result of Kim, and Lovejoy. All right. Further refined results are also true using similar analytical techniques that we used, but I'm not going to state those results here. So let's see some of the references of what I have been mentioning. So this is the first paper of Kim, and Lovejoy, which appeared in the European Journal of Combinatorics last year. And the second paper of Kim, and Kim, it is online in the Bulletin of the Australian Mathematical Society. So, I mean, as a general reference for partitions for students, they can take a look at Integer Partitions by Andrews and Erickson, which is a very short book, about 150 pages long. But it's a nicely written book for beginners. And for more advanced stuff, then there is this book by Andrews, which is called The Theory of Partitions. So now we are, 2/3 of the way done. And if there are any questions, then I can take while you take a look at this very nice picture of the Mediterranean coast.
I did have one or two questions if you don't mind.
Yeah. Yeah.
I guess I was just wondering what was known about the sort of is there anything known about the limiting behavior of those predominantly even and odd partitions? For instance, is it, in every example you gave, sort of it seemed like it was the first number that wasn't in the set S that was controlling, sort of which with the even or odd one sort of got bigger in the limit. Is that known, or let me put it in the chat. Maybe that's a little easier to see.
Okay, I see that. Okay,
Yeah.
so is it known for finite? Yeah. Yeah, it's not known. So I mean, as far as I know, that this is not known. So
okay, thank you.
Asking. I mean, it would be interesting to actually find this sort of results. So I mentioned this at the end, actually, some open questions for, yeah.
So, are you going to show some proofs or?
Yes, I'm going to show. So this is just like a intermission. All right, so let's move on to the next part then. Right, so what about the proofs? No, so the papers by the Kims and Lovejoy, they proved all of the results analytically. I mean, most of the results analytically. So there were some bits and pieces of combinatorial proofs. The first team, that is Banerjee, Bhattacharjee, Dastidar, Mahanta, and me, we gave combinatorial proofs for our results. All of our proofs were combinatorial. And in the second team, we gave only analytical proofs for our results. There was not much combinatorials going on. Our techniques are actually similar to the ones used by the Kims and Lovejoy for the analytical proof. So in the sequel, we need some notations to make our life easier. So these are the Q Pockhammer symbols, or the Q rising factorials, if you wish. So AQ sub n is now this product, 1 minus AQ to the n minus, sorry, this should be K, okay. 1 minus AQ to the K minus 1. So this is a product of n factors. And AQ sub infinity is now just the infinite version of this product. Again, this should be a K. It's not an N. All right, so we need these two notations to make our life easier. So if you put, yeah, I mean, I'll show it when it comes. Okay, so let's look at the analytical proof techniques, and then I'll say a little bit about the combinatorial proof. So now let us denote the generating functions for Q sub E of n and Q sub O of n by capital Q of Q, capital Q sub E of Q and capital Q sub O of Q. Then we can prove that these generating functions takes the following form. So this is capital Q sub O of Q is now of this sort, of this form, and capital Q sub E of Q is of this form. Okay. So unfortunately, I should have mentioned more terms because our result is only true for from n greater than 7. Anyway, I think because of the space, I did not write. Yeah, so I mean, at first glance, this looks a bit complicated, the results, and I'm going to explain how we can get these generating functions. But to prove our results, we need the difference of the generating functions. And if you take just naively, if you take the difference of these two generating functions, then you are not going to get nice forms to do some analysis to get the inequalities. So we need to do something to these generating functions. But first, let me explain how the generating functions occur. Okay. So let's look at a much easier case. So by standard combinatorial arguments, we can prove that this particular quantity q to the power b of n divided by q square sub n is the generating function for partitions with at most n even parts when b is equal to 0, exactly n odd parts when b is equal to 1, and exactly n even parts when b is equal to 2. So how does this work? So let's look at b equal to 0 case. Okay, so that means we want to show that 1 over q square n is the generating function for partitions with at most n even parts. So it is easy to see if b is equal to 0. We just reinterpret each part as sums of 2. Okay. So for example, if this is a partition 6 plus 4, then we just reinterpret this as 2 plus 2 plus 2, which corresponds to the part 6, and 2 plus 2, which corresponds to the part 4. So we just break it into 2s, and then each 2 will contribute q square to the product. So we can see that 1 over q square n will now be the generating function, because there are at most n parts. So we have this n. Okay. For b equal to 1, we just add 1 to each part. So if we just add 1 to each part, then out of these partitions where these were partitions with at most n even parts, we'll now have partitions with at most n odd parts. If we add just 1 to each of the part. So there might be some zeros which will contribute to the number of parts. Okay. And if there are less than n parts, then we just append a 1 to these zeros, so that we make exactly n odd parts in this case. And each of these ones will add a factor of q to the n. So there are n ones which have been added, so it will add a factor of q to the n to the earlier generating function. So that q to the n divided by q square n will now be the generating function for exactly n odd parts, partitions with exactly n parts. And the case b equal to 2 is similar. So here we need exactly n even parts. We just add 2's instead of 1's, like we did in the previous case. And if there are less than n parts in the first case, then we just add 2's, so that we make it into n parts. Okay. And this will add a factor of q to the 2n, because we're adding 2 and because we're adding n 2's. So it will add a factor of q to the 2n. Okay. Now let's look at our generating function. So recall that q sub O of n is now the number of partitions of n without the part 1, where the number of odd parts are more than even parts. And I said that the generating function for q sub O of n was this difference of two generating functions. So one can think of such partitions as actually pairs of partitions with only odd and even parts respectively. Okay, so I can break this. So if I have a partition lambda where I don't allow the part 1 to appear and the number of odd parts are more than even parts, then I can break this partition lambda into two different partitions where one partition will only have odd parts and the other partition will only have even parts. So into mu and nu, with only odd parts for mu and even parts for nu. Now the first sum, this sum, it is just counting the number of such pairs, mu and nu, where the number of parts in mu is n and that in nu is at most n. Okay, so that means the number of parts in mu, that means odd parts is n exactly, and the number of even parts is at most n. Okay, so this is now just a product of q to the 2n divided by q square n into q to the n divided by q square n. Okay, so this is just product of two of the earlier terms.
You're putting 3 to each part, is it?
Yes, I'm putting 3 to each part in this case. And I need to now subtract the partitions where they have equal number of parts. That means I now subtract where they have equal number of odd parts and even parts, which is n. Okay, so if I do that, then we'll get this other quantity. Okay, so this is how we can get the generating function for q sub O of q.
So
what about?
Sorry, how do you get the equal parts here? Equal.
So equal parts, because here I'm counting at most n. So it also counts the number of partitions where there are n even parts. But in our case, I don't need the number of odd parts and even parts to be equal. So I have to subtract the number of partitions where odd parts are also n and even parts are also n. Sorry, you were on mute.
How does 5 come in there?
Oh, this is q to the 3n times q to the 2n in this case. So q to the 3n over q square n is one generating function, and q to the 2n divided by q square n is another generating function, which I am just multiplying now. And I'm summing over all that.
I see. Okay, thank you.
So for what about the other generating function, q sub e of q? This one is easier, because if I don't allow 1 as a part, then the generating function for all partitions will just be the first term. 1 over q square q infinity is just the generating function if I don't allow the 1 as a part. And I just subtract whatever I don't need now from the number of all such partitions. Okay. So we have these two generating functions, and as I mentioned naively, if I want to subtract, then I don't get what I want. So we have to use some classical Q series identities to transform the above generating functions into nicer forms, and these nicer forms are given below, given in this slide. So I can transform Q sub O of Q into this quantity here, and Q sub E of Q into this quantity here. So we use Hyness transformation to do this, which is a classical Q series transformation identity. So once we have this, then it is easier to now subtract because we see that these are similar. So whatever we have in the sum, these are similar now. And if we subtract this, then we just get this quantity. Now, from here, it is not very difficult to get the non-negativity of the coefficients. So we need non-negativity of the coefficients, basically. So clearly, for the summons from n equal to 2 onward, the coefficients are positive, because if n is equal to 2, then this will, or I mean, if n is greater than 2, then this 1 minus q to the n will get cancelled either from here or from here. Okay. So whatever is remaining will now only yield positive coefficients if this is cancelled. So this I have explained. If n is even, then 1 minus q to the n will be cancelled by a factor of q square n from here. And if n is odd, then it will be cancelled out by a factor from here, q to the 3 q square infinity. For n equal to 1, we again have to use some other classical Q series identity to get non-negativity. It's not very, I mean, it's straightforward, but it takes some amount of time to explain. So here we have to use, for those who know, we have to use a identity of Sylvester to get the non-negativity of for n equal to 1. And then we are done. If we do this, we are done with the proof for the restricted partitions, biases for the restricted partitions case. Now, what about the combinatorial proof techniques that I mentioned? That some of the proof techniques that we had were combinatorial in nature. So the fundamental principle behind our proof is the following for the combinatorial proofs. So we are given two sets, X and Y, and our goal is to prove that the cardinality of one set is bigger than the cardinality of the other. So here, let's consider that the cardinality of Y is greater than the cardinality of X. Then we choose a subset of X and define an injective map from that subset to Y. So here I am denoting that subset by X naught. So from X naught, we define an injective map to Y. Then to prove that this cardinality of Y is greater than cardinality of X, it is enough to find or to prove for a suitable subset Y naught of Y minus F of X naught with Y naught is greater than X minus X naught. So it is enough to prove for a suitable subset Y naught that we have this here. Then we are done with the proof. So these maps, the map F that I have written here, these are actually quite intricate maps. So it's not very, it's not one map actually. So we have to further subdivide the set X naught that we take into more subsets, and then we have to define a map on each of these subsets and so on. So I don't want to do the proof here because it takes a lot of time. Even in printed pages, it's about 6 pages. So I mean, but the general idea is this. So we find an injection from a subset of X to the set Y. Right. So there are many open questions that can be asked about all of these parity biases and other things that I've discussed, and some of these I would like to share. So so if you remember, there was this result by Kim and Lovejoy about distinct parts partition, where we don't restrict the number of parts, and I said that we have proved this using combinatorial techniques. So a natural question would be to ask about the distinct parts partition where we restrict the number of parts. So if one does not appear as a part, what happens then to the distinct parts partition? And limited data suggests that here the parity bias is not as straightforward as the other case. Here the parity bias is actually in 2 directions. So if we take only even integers, then the distinct parts partition of n with the part 1 not allowed, where odd number of parts are more in number than even parts, is greater than the other quantity, where even number of parts is greater than odd parts. And this inequality is reversed if we just consider the odd integers now. So these are actually the distinct parts analog of Q sub E and Q sub O of n. And I mean, we don't have a proof for this. So yeah, this is an open question. Then one question that was asked also by Peter, and a similar question in a similar flavor is the following. So I mean, is it true that P sub O of n is always greater than P sub E of n if we restrict parts, like if I restrict the part K where K is greater than 2? And for certain cases, I have done some, I mean, very limited data again, not too much. So for certain case where I have checked, this is always true. And what about if I include 1 to the K, then this inequality is reversed. Intuitively, it is clear again, because if I remove 1, then a lot of parts are removed from the partition. A lot of odd parts are removed from the partition. So for this case, it seems that for each K, there exists some number n of K, after which point this inequality is always true. So can it be shown for a certain case that this inequality is true? And it would also be worthwhile to understand this threshold n of K asymptotically. So when for which K, I mean, how does it depend on K and how does it depend on n and so on? So more questions. So there have been more developments on this topic. So Shane Chern, he recently studied more general biases in arithmetic progressions. So if you remember, we discussed Kim and Kim's result, where they discussed biases in arithmetic progression, where they took P sub j k of m, but they only studied for j and k equal to 0 and 1. And Chern, he actually extended these cases for all j and k. And can our techniques be extended to his case? So I think that the analytical techniques can be done, but the combinatorial techniques still look very difficult. The Chern's paper is also interesting because he uses he does this in two separate cases. So for j and k equal to 1 and 2, he does this combinatorially, and for all the other j and k's, he does this analytically. So his analytical proof might also be extended to our case, but the combinatorial proof, I don't think it can be done. Anyway, so as I mentioned already in the talk, that Kim Lovejoy and Kim, they also studied asymptotics for all of their quantities, P sub E, P sub O, and P sub jk of m. So such asymptotics would also be interesting for other functions that appear in this talk, which we have not studied so far. And the last question would be, can our analytical proofs be done combinatorially, like we did for the case of Kim and Lovejoy's proofs? So that's all I have. Thank you so much for your attention.
Thank you, Manjil. Very nice talk. Any questions or comments for the speaker? So, Manjil, I have a question. This proof technique that you described, you take X naught and then you basically wipe it off, and then so I mean this is very much like that involution kind of principle, right? Where you go in several places.
Yeah. So I mean, yeah, well, not exactly. So yeah, I think it's so involution is a bit more difficult to understand in first glance.
My question is, have you tried? I mean, there are other positivity questions, right? Which are begging a sort of combinatorial proof.
Yeah.
Line type of stuff.
Yeah. So I have not tried, to be honest, because already this was very difficult.
Yeah.
So
I mean,
yeah. So
but have you seen this kind? I mean, this is a new type of argument, or is it something you've seen before?
It's not exactly new. So it combines ideas from other places that I've seen this used.
All right, thank you. Very nice talk. Any other comments or queries?
So about the positivity thing, actually, Chern's, so I mean, you might be interested in this. So Chern's paper has some positivity conjectures at the end. He mentions 2 or 3 other positivity conjectures for Q series, not related to any combinatorial identities.
Any comments? Or I think Professor Ajit Iqbal Singh, you had a comment earlier in the chat.
Yes, I had a comment, that somehow we needed to break up a number S into 4 parts, S1, S2, S3, S4, such that S1, S4 is S2, S3. And then we had to find various ways of doing them. And this was very useful in studying quantum entanglement of resonance valence bond states. So do you have any such theoretical results also for a
No.
fixed number of parts?
Oh, okay. Yeah, no, not really. We don't have for any fixed number of parts. But yeah, it would be interesting actually if I fix the number of parts to some number. Yeah.
Maybe you can stop sharing.
Oh yes.
And then related to matrix theory also, like we needed that matrix S1, S2, S3, S4 to be non-singular, actually to have rank 1. Okay. And that is what we needed for quantum entanglement properties. And then if you take different partitions, then the different parts of the state get attached to it. And we needed all such computations.
Okay. Yeah, I mean, I have not tried to restrict the number of parts and ask this question.
Thank you. Thank you. Wonderful talk.
Thank you.
Okay, any other comments or queries? Okay, let me just